All right. Hello and good evening, everyone, and welcome to Science in the Mountains. My name is Brian Fitzgerald, and I'm the Director of Education here for Mount Washington Observatory. Thank you so much for joining the program tonight and joining us this evening to share their current research projects at the observatory. Our summit interns, Peter Edwards, Mary McDonald, Mason Branson, and Frank Vazano. Thanks so much for joining for tonight. And for those of you who aren't already familiar with the observatory, Mount Washington Observatory is a private nonprofit organization supported by members with a mission to advance the understanding of the forces that create Earth's weather and climate. And the way that we do that is through operating our around-the-clock weather observations from the summit of Mount Washington and beyond, by conducting research and product testing projects, and by developing and offering innovative educational programs. If you have questions for tonight's speakers and you're joining us via Zoom, by all means, get your questions in at any point in time here. We will be collecting those throughout the program, and we'll be sure to leave some time at the very end to make sure that we get as much time as possible for a live Q&A session. If you're joining us through another means and want to join us for a live program on Zoom, make sure to sign up for a program over at mountwashington.org. You can join us that way. So before we kick things off, I would love to share a poll here made of questions that our speakers have put together for you this evening. So we'll go ahead and launch that if you're joining us over Zoom right now. So right now we should be seeing a poll pop up into your screen here with 4 questions for tonight's program here. The very first question, always curious where folks are joining from tonight. And if you're joining from a state within New England, perhaps you're joining from somewhere outside of the region or perhaps even outside the country, please, by all means, get your questions in here. The second question here. So on average, when do the heaviest upslope snow showers, these are mountain-induced snow showers, when do they typically occur on Mount Washington? Is it midwinter, late spring, during the shoulder seasons, or perhaps during the summer? The next question, what air temperature is best for creating the fluffiest snow? I.e., what are the temperatures that are occurring in the cloud when snow is forming? Is it 32 Fahrenheit, 10 Fahrenheit, 20 degrees Fahrenheit, or is it 5 degrees below 0 Fahrenheit? Get your answers in there, your best guesses, or perhaps you really know these answers, including this last one. You get bonus points if you get not only the total right, but also the year here. What is the most snowfall recorded on the summit of Mount Washington during a winter season? Is it 566.4 inches, 521.5, 602.1, or an even 899 inches? All right, I see quite a few of you have responded to the poll. We'll give you just another few more seconds here to get your responses in, and we'll close it out in 3, 2, 1. All righty, we'll end it right there, and we'll share out some results. All right, well, the Granite State is well represented here, almost a third of you joining from New Hampshire. Welcome, welcome. Everywhere from inside of New England is represented as well, and even outside the region, almost 20% of you. And then we have 3 folks joining from outside the country as well. Welcome to all of you, regardless of where you're joining from. All right, on average, when do the heaviest upslope snow events occur in Mount Washington? 49% of you said during the shoulder seasons. Second place there during midwinter, January, February. All right. Next question, what air temperature is best for creating the fluffiest snow? Well, most of you said 10 degrees Fahrenheit, about 36% of you, with 20 degrees Fahrenheit being the runner-up there. And then finally, the most snowfall in a recorded season on Mount Washington. More than half of you said 602.1 inches. Alrighty, remember you get bonus points if you also share the year in which that happened, or I should say the years. Alrighty, we'll go ahead and stop sharing there because I don't want to give away these answers. You're going to have to hear them from our speakers from this evening. And without further ado, I'd love to welcome our first speaker, first of 3 for tonight, our first of 3 projects, Peter Edwards, one of our summit interns. Peter, are you there? Hey, Peter.
Hi. Hi, everyone. My name is Peter Edwards. I'm one of the some interns at the observatory this winter, and I'm currently studying atmospheric science at the University of Massachusetts Lowell. My presentation topic tonight and research project that I'm currently working on as part of my internship is upslope snow. Why I chose this topic and how I formed my hypothesis was actually based on a personal experience I had in the White Mountains. So I'm going to quickly share a story. I think seems like a lot of you are from New England or maybe familiar with the mountains themselves. So it's a good way to lead into my project and also a relatable story. So last year on New Year's Eve during my winter break, I was looking at weather models and noticed that the weather was clearing with high pressure moving in to the northeast, or at least so I had thought it was clearing. So I packed up my gear and drove up to the mountains the next day, expecting clear weather. But as I arrived at the trailhead, it was snowing lightly. I didn't make much of it at first. I was thinking maybe it was just an isolated snow shower that passed in after the storm and the sky would quickly clear as I started hiking. But as I continued to go up the trail, the snow got heavier and heavier. The drifts got deeper and deeper. And I quickly realized that this was not a passing snow shower, and this was more something stationary, a stationary system over the mountains. What I was unknowingly experiencing at the time was actually upslope snow. And then eventually I got to my campsite, got into my sleeping bag, set up my tent. And the first thing I felt was some embarrassment because as a meteorologist, getting caught off guard by the weather hurt my ego a little bit, probably. Definitely is just kind of embarrassing in general. But as I was laying there, I was hearing the wind rush over my head, and I eventually realized that the culprit was upslope snow. I'd heard of it before, learned about it in my meteorology classes a little bit, but it didn't dawn on me at the time, and nor did I see it showing up in the models. So I got up there and got soaked because as I was sweating going up the mountain, the snow was melting on my jacket, and it made it a pretty miserable experience. But as I was laying there, I started to question how I missed that and what variables and what I wasn't seeing on the models or seeing in my analysis the day before I planned my trip. And I just began to wonder more about them and how impactful they are to the snowpack on Mount Washington and the White Mountains in general. Then I began to think about it in the context of climate change and began to wonder if it was increasing or decreasing over time and how that could impact the total snowpack on the mountain as we look forward into the future, or in the past in this case. And needless to say, that experience stuck with me, and it led me to build out this 20-year climatology of events and in an attempt to answer those questions for myself. So let's get into the slideshow here. There we go. So first thing I'm going to go over is like what are the main ingredients for upslope snow, or the most important anyway. Four essential ingredients I would say are obviously cold air. You need cold air to make snow. And then you need northwest or westerly winds that rise up the mountain slopes. And you also need moisture or high levels of humidity. Moisture and humidity are going to be used interchangeably here, but you need that moisture and humidity deposited at lower elevations. And then also a stationary or slow moving weather pattern is optimal for bigger upslope snow events and upslope snow events in general. So I'm just going to move my bar here. I can't see my own slides. Anyway, so what is upslope snow and how does it occur? The biggest criteria that differentiates upslope snow from other snow is that it's precipitation event that is specific to the higher terrain. Occasionally, it can bleed out into lower elevations. You might see a little bit of snow at the lower elevations when these are occurring, but most of the time, the heaviest snow and the biggest impacts are going to occur at the higher elevations. So a storm will generally pass by like a nor'easter or like some of the bigger rain events I'm sure many of you are familiar with that have occurred in the last several years on Mount Washington that result in thaws. Those will pass by as the cold front attached to the storm passes through. The winds will start blowing out of the west or especially the northwest. And then the mountain range acts as a physical barrier to those winds and kind of forces the winds to stop and not necessarily stop, but slow down and start moving up the slope. The winds then pick up moisture from the low elevations that was deposited from the storm and drives it up the slopes as well. If these ingredients stick around, the mountains will continue to get snow as long as these conditions persist. And quickly, just a kind of a precursor to some of the other stuff we'll be talking about is The best setup for upslope snow is a storm that's stalled or stuck to the northeast around the Canadian Maritimes or southeast Canada, to put it more generally, in high pressure building and moving in from the west. This combo gives us strong northwest winds and the potential for upslope snow, and also can indicate that the pattern is moving slowly, and we'll be able to generate more upslope snow for the duration of the event. This is just a very rough diagram. The star obviously represents Mount Washington, the red lines just kind of giving us a general direction of the wind when we get these upslope snow events. Here's just a diagram from the National Weather Service. Kind of goes into a little more technical detail on upslope snow. The blue arrow is showing you basically where the winds are traveling, where the air is moving and rising up the slopes. So when the wind blows against the mountains or the hills, it is forced to rise. This is also called orographic lift. And it isn't specific to winter, but obviously for this presentation, we'll be talking about upslope snow, which is specific to winter or cold seasons in general. And as that moist air rises and cools, the water vapor condenses, resulting in clouds and precipitation. This results in the windward side of the mountain receiving more snow than the surrounding areas during the winters and during the full year in general. So one thing I want to get into is a case study, so we can kind of take that information and look at some weather maps and look at some data and try to figure out what weather patterns actually cause these. So if you're going into the mountains, maybe you can see your weatherman showing you a chart similar to this, I hope. Hopefully you've seen one similar to this, so you can find out when these are going to happen for yourself. So as you can see in the top right, there's these white bars called isobars kind of circled around each other. Isobars are just representation of the pressure differences throughout the atmosphere. And this L, I hope you can see right here, is representing low pressure, or that storm system that had moved through and is now anchored over the Canadian Maritimes or in southeast Canada. And to your left here, on the left side of the image, you have pretty potent area of high pressure, pretty sprawling area of high pressure, stretching from northern Canada in Hudson Bay all the way down into the Central Plains. As that moves in, the pressure gradient, or these isobars want to tighten, and more air is forced to rush through those large pressure deviations. And that gives us a really strong northwest wind. And for this particular event, we had pretty potent northwest winds, not the strongest, but all the ingredients were there for a sustained upslope snow event. I'm just going to go through a couple of charts. These might be difficult to read if you're not familiar with looking at weather models, but I'll try to go over them as best as I can. The blue on this chart on the left, and the red is representing the pressures. The blue pressures are lower pressures in the atmosphere, and the red are higher pressures. And also a star is marking Mount Washington for reference. So the blue on the left-hand side is representing low pressure at roughly 20,000 feet in the atmosphere, or we consider that pressure level roughly 500 millibars. This low pressure at this height in the atmosphere is kind of anchoring that storm in place, keeping that storm stationary and allowing the winds to blow to the northwest for a longer period of time. And the chart on the right is showing the pressure levels at 850 millibars, or 5,000 feet, so roughly right below summit level. And this would represent more the surface cyclone, or the storm at the surface that's impacting us directly. And as you can see, there's winds wrapping around the storm, coming out of the northwest and rushing into and over Mount Washington. And now these two charts are, one on the left showing the average wind speed, which was roughly 20 to 25 meters per second, 40 knots, or right around 50 miles per hour on average for the two-day event from October 15th to October 16th. And on the right, you can see the blues. Obviously, the darker shades are the higher levels of humidity in the atmosphere. In this case, it was roughly 95 to 100%. So we had almost complete saturation in a deep reservoir of moisture for upslope snow to continue happening and for large amounts of upslope snow to occur during the duration of the event. And just a quick event recap. Overall pattern was consistent with most upslope snow events on Mount Washington. Cold air moved in after the passage of the storm. Once that cold front moved through, and strong and sustained winds out of the northwest due to the stalled storm and the high pressure to the west. There was high levels of moisture present at the surrounding low elevations. Again, just that reservoir. So as the winds keep blowing and keep pushing the air up the slope, it can grab ample moisture to continue condensing and continue producing snow. And over the course of just 2 days, 7.6 inches of snowfall fell during the course of the event, which, based on the winter warning weather criteria by the National Weather Service in the local area, that would be considered a winter storm. That would meet criteria for a winter storm warning. So this would be a heavy snowfall event. And now I'm going to get into my research project and just kind of summarize it in a little more detail. So I looked at 20 years of upslope snow events on Mount Washington. I determined the upslope snow events by looking at the lower elevation stations in the area, Whitefield, where the airport is, Freiburg in Maine, and then Berlin, which is north of the White Mountains. And I compared that to the snowfall data on the top of Mount Washington. And if it was snowing on Mount Washington and wasn't snowing at those stations, I could then pick those events out and determine if it was upslope snow. I'd have to do a little more research to confirm because the station data isn't perfect. And there can be other events or things going on in the atmosphere that might cause that discrepancy and could mislead me. But for the most part, it was pretty good at picking up on a large amount of events over the last 20 years. And then with that data, I was able to determine how often upslope snow events happen seasonally and yearly, and then determine how much snowfall they added to the mountain overall. And like I said, I used weather data and specifically surface analysis, like the map I showed you earlier with the low pressure and the high pressure on it, and all the isobars. I used those to help me drill down on the events and make sure that what I was seeing in the data was an upslope snow event. My results for my project, the blue line at the top represents the total annual snowfall for each year on Mount Washington. On the x-axis at the bottom, each year is its own data point or its own point on the x-axis, and on the right side represents a percent from upslope snow, which you can see in the green dotted line, and then when the red line at the bottom is the amount of upslope snow per year. So when I looked at this data, I was surprised. I thought upslope snow would be slightly higher contribution, maybe the 25 to 30% range annually, but ended up being more in the 18% range. I think it's probably closer to 20 because some events were just too hard to determine. Either they were very low amount of snowfall, or in some instances, a storm would pass through and immediately transition to upslope snow, and it was difficult to go back in the data and figure out when that exactly happened to get an accurate measurement. So I had to get rid of a few events. So I do suspect it's probably in the 20 to 22% range annually, at least in the last 20 years. And over the last 20 years, seen an average of 1.03 inches per year increase of upslope snow, which is consistent with the overall trends of snow in Mount Washington. Going back, even back into the 30s and 40s, we've been seeing a slight increase in snow in Mount Washington over the course of the data set. And I just need to add a caveat. This is only a 20-year climatology. I couldn't build that out further just to lack of data availability, but I think it's still interesting to see that my hypothesis at the time that upslope snow was maybe increasing with global warming as you have a warmer atmosphere, especially getting warmer in the valleys, which is represented in the data as well, that with warmer air, you can hold more moisture within the air, and that's going to create a deeper reservoir when the cold air moves in at higher elevations for upslope snow events. Can I confirm the hypothesis here? Not quite yet, but Perhaps one day I will. One day I will, as I keep researching this topic further. And then I categorize the events based on the month in total snowfall. And this is where we'll get the answer for the multiple choice question you did at the beginning. The shoulder seasons, and I was very surprised everyone got that, and very excited as well that everyone was able to answer that. I thought more people would pick winter. Both are good guesses, as you can get heavy upslope snow events really anytime, October through May, but the heaviest upslope snow events tend to occur in the shoulder seasons. Probably because the air is a little bit warmer in general. There's more moisture storms are bringing up, and you're able to just have longer upslope snow events. And the weather patterns also tend to be a little slower and more stationary in those times of years. And like I said, they were categorized based on the local winter weather criteria, warning criteria. So light was 1.5 to 3 inches, moderate was 3 to 6, and then heavy was 6 inches. And overall, the events are distributed heavily in the light category. There's fewer moderate, and then pretty seldomly you get these heavier events. And the main takeaways, although a long-term climate trend can't be determined from this data, an increase of 1.03 inches per year since 2005 is still notable in my opinion. And this work could enable longer-term climate studies to be performed regarding upslope snow in the future, and could also enable future interns, students, or researchers to look further into the meteorological dynamics and impacts of upslope snow on Mount Washington and the White Mountains in general. And that is the end of my presentation. And thank you. Really happy to have everyone here watching. That was awesome.
Thanks so much, Peter. Really appreciate it. And without further ado, as I mentioned, we'll save questions for the end here. But Peter, thank you for sharing, and we'll transition over to the summit of Mount Washington with the interns who are on shift right now. We'll have Mary McDonald and Mace Franson present next. So thanks, Peter.
All right.
Yep, thank you.
Hi, everyone. Thanks for the introduction, Brian. Marin and I are very excited to be presenting from the summit of Mount Washington, here to tell you what we've been working on this summer, which is a climatology of the solid to liquid ratio of Mount Washington. Just share our screen for a second. Share. There you go.
Great. Awesome. So first, before we really get into the subject that we're talking about, whoop, sorry everyone. Let's make sure that will scroll. What is the solid to liquid ratio? This is a way that meteorologists measure density. It's an inverse for density, and basically how that's calculated is you take the amount of solid accumulation that you have on the summit, so that could be sleet, snow, hail, grapple, all of that, and then you divide it by the amount of liquid equivalent that you get when you melt that precipitation down. So for example, if I have 10 inches of snow that I have collected and I melt that down and I get 1 inch of liquid water, I would have an SLR of a 10 to 1, which also corresponds to a 10% density. Most of the time, a standard SLR value of 10 to 1 is used. This is used in a lot of quantitative precipitation forecast models. So for example, any model that you use that is outputting projected snow totals for storm events, a 10 to 1 is usually being used for that. And that's a standard that's been set by the National Weather Service. In addition to helping with quantitative precipitation models, understanding SLR can also be really helpful when you're looking at snow characteristics. So for example, looking at seasonal density or determining how much snow you have present and what that means for your watershed health or your stream totals later on. All of those things SLR can help in determining. And the reason why SLR is used as opposed to density or the snow water equivalent, like is used by hydrologists and others, is because with most quantitative precipitation forecasts, you actually are looking at the amount of liquid water that is available in a cloud to precipitate. And so it's almost working backwards from density, where you start with the water and you want to know how much snow or solid precipitation you have in return. So being able to understand SLR, especially in an area where we get so much snow variability, is really important here on the summit.
So before we get into things, I should introduce a little bit more about how we measure snow on the summit of Mount Washington. As Marin said, the weather's pretty extreme up here. And a lot of the time that can lead to issues when measuring snow. So when the weather's good, usually we measure every 6 hours, and that's called a synoptic. When we go out to the precipitation can, which is centered on the summit, like the video is showing, and we exchange the cans. We bring it inside, and we actually use the ruler that I'm using as a microphone stick to measure the snow depth and melt that snow, and then measure the liquid equivalent, and then use that to calculate the SLR. The issue is, because the weather is so extreme up here, a lot of the time things go wrong. There might be ice falling in, or the wind is blowing so strong that none of the snow actually ends up in the can. And when that happens, we have to estimate. And something we're interested in is trying to figure out how observers are estimating, if that's a representative of the SLR that we're experiencing on the summit in general, and if there's maybe any bias in that. And for those who answered the trivia question at the start, the most snowy winter that we ever got up here was in 1968 to 1969, and we got a record 566.4 inches of snowfall. All right.
That must have been a lot of snow to measure from the precip can. Oop. All right, come on. Does not want to go. Sweet. So we have this data record at the summit that is pretty extensive. I mean, going back all the way to 1934, which is pretty insane, especially for things like snow, which are insanely variable, or just solid precipitation in general. So this study is using our extensive data record to actually look at the SLR of snow on the summit, because snow is a pretty variable thing, and using a standard 10-to-1 like the MWOBS does may not be representative of the snow that's up on the summit. And we want to see if it is representative, and if it's not, what is influencing the variability of SLR up here. So for us, that means looking also at our record of temperatures and wind speeds to see, are those impacting SLR values? Are we having denser snow certain times of the year, lighter snow certain times of the year? And what does that mean for the overall, I guess, watershed that is the Cutler drainage, as well as all the other drainages that the summit feeds into? We also want to look at how estimates are impacting our record. Because observers do occasionally have to estimate, we want to know, are those representative, and are they impacting our climatology? And if they are, what impact do they have?
So as Marin mentioned, our data set goes all the way back to 1934, since the inception of the Mount Washington Observatory. But we're only using data from 1980 to 2024. The reason for that, for those familiar with the Mount Washington, the Sherman Adams building was built in 1980. And because of that construction, the precipitation can was moved to a different location. And so in the interest of comparing apples to apples and not apples to oranges, we're using 1980 to 2024. So all of the data is homogenized and using the same precip can location. And then we're also using daily data, so daily averages for wind and temperature, and then the 24-hour accumulation for solid precipitation, and then the associated water equivalent. And then we're interpreting the snow year, which starts in October and goes through till the May of the following year. So we're looking at one consistent snow season. So that's the data set that we're using. For filtering, obviously, observational data is hardly ever perfect. And there's a lot of instances where things might go wrong. So we're filtering out any instance where solid precipitation was less than ½ an inch, which is following the standard methodology for SLR research from literature. And then any instance where the liquid equivalent is greater than the solid precipitation, which intuitively, when you think about what SLR means, doesn't make a lot of sense. You can't have the melted snow be more than the snowfall that fell. So any of those instances we're filtering out, and then all of the other cases, we're just calculating the SLR and using that data in our research. And then separately, we also have a record of every single estimate that's been taken for this period from 1980 to 2024. And so we're going through that record and looking at any date where an estimate was taken and accounting that, and having two separate data sets that we're running in tandem for our analysis, one including the estimates and then one with the estimates excluded. And that way we can interpret what effect the estimates might be having on our climatology and any other analysis we might do.
So before we got into the nitty gritty, we first really just wanted to see, what does our data look like? We want to know what the distribution of SLR values on the summit looks like. So seeing which values are more common, what occurs more often. And we did that by using histograms. So you can see here, for all of these figures, we have our count of days of values recorded on our y-axis. So for example, we have, about 300 counts for an SLR of 8. So that means that there are 300 days in that 1980 to the 2024 period where we had 300 days where SLR was recorded to be 8. Then we have on our x-axis, we have solid to liquid ratio in that first figure. So that spans between 1 to 1, meaning that for 1 inch of snow, we had 1 inch of water, all the way up to 50 to 1, meaning that the snow was so light that if we had 50 inches of snow and we melted it down, it would only make 1 inch of liquid water. So think really light, fluffy snow. For our wind speed, we have just a standard wind speed in miles per hour on our x-axis. And then for temperature, we have just temperature in Fahrenheit. You can see from all of these, we have different distributions for each of our variables. For SLR, we don't have a normal distribution, which means that we don't have like a perfect bell curve like you would expect for nice, very evenly distributed data. And what that means is that we find that the median is a more valid center of mass for our data. And when looking at the median value, you can see that up in the right corner of that first figure, it's about 8.6 to 1 for our SLR, which means that it is below that standard 10 to 1 set by the MWOBS. You can also see we have estimates in white there, kind of at the top of each bar, and that's to show that with and without estimates, we don't have a huge difference in our data set. There's not a difference in distribution, it's all pretty even, and that shows that estimates initially don't seem to have a huge impact on SLR, meaning that we don't have a greater amount of estimates at a certain value. Looking at wind speed, we have a slightly more even distribution. That makes sense based off of our average winter wind speed, which is about 45 miles per hour. And again, our estimates are pretty evenly distributed throughout that bell curve. So there's no wind speed initially that appears to have a greater amount of estimates needed for that wind speed. Temperature is also a little bit skewed, which makes sense based off of our average winter temperatures. And again, that's for October through May. And you can see, again, those estimates are pretty evenly distributed. So we don't have one specific temperature that is requiring observers to estimate more. Ultimately, this shows us that we do have a pretty varied distribution of SLR, and that standard 10 to 1 may not be the most representative for snow densities up here on the summit.
After that, we assembled the climatology, and that's what we're looking at here. These are 3 figures much the same way, where it's SLR, wind speed, and temperature in that order for the climatology, meaning that on our x-axis, it starts in October and it goes through till May at the end. For the SLR, as Maren mentioned, it's varied, but typically under 10, under that NWS standard of 10 to 1. And what we notice is that in the first couple months of winter, from October to about halfway through December, SLR has an increasing trend where from October to December, it's increasing from 5 to about that median 8.5, 8.6, which sort of intuitively makes sense. In early fall, those fall storms tend to have wetter, heavier snow, so that corresponds to lower SLR values. And then as you get deeper into winter, that snow gets drier, it gets fluffier and more powdery, and those are the higher SLR values that you're seeing. And then from December through until roughly halfway through March, SLR values are pretty consistent, and they're pretty consistent around 8.6. And then after that point, through the rest of the snow year, SLR is decreasing again back down to that 5. What we notice about temperature, I'm skipping ahead to the third figure, is that it's sort of the inverse relationship, where it initially starts high and decreases, which we would expect, right? You would expect temperatures in October to be a little bit warmer than you would in January, typically. And then In the middle of the winter from January, February, and March, temperatures are pretty consistently just above zero, around 5 degrees, and then experience an increasing trend. And so intuitively, you might expect a correlation between SLR and temperature from this climatology. And then lastly, wind speed doesn't look like either of the other two plots. It's pretty much consistent throughout, right on that median 45 miles per hour mark. We're also plotting both estimates and non-estimates, much like the histograms. And what we're noticing, the lines are very similar. And in fact, it's hard to tell that we're plotting estimates at all in some cases. And what that tells us is that estimate and non-estimate data are highly similar. And at least from our climatology, when we're aggregating across the whole time series, estimates don't really have to have much of an impact on our climatology at all. So that indicates that our observers are doing a good job, and they're when they are estimating SLR, it is at least representative of the snow density that Mount Washington experiences.
So it's one thing to be able to look at the climatology and see these potential correlations between SLR and wind, temperature. But to confirm that, we actually wanted to look at some linear regressions as well. So here you can see we have two figures. On the left, we have wind speed versus SLR as a linear regression. So on our x-axis, we have wind speed, and on our y-axis, we have SLR. And you can see that the trend line there isn't super strong. We almost have a flat line, and there's not a huge difference between estimated and non-estimated data. But you can see here that kind of confirms that there's not a correlation between SLR and wind speed, meaning that it doesn't really matter what wind speed it is. SLR is independent of that. You can also see that all of our data points are clustered into one area. There's not really a separation between estimates and non-estimates. So again, that confirms that there's not really a certain wind speed where estimates are being accounted for more, or a certain SLR where estimates are being accounted for more. They're all kind of just homogeneous, all combined here in this blob. And then looking at the figure on the right is temperature versus SLR. So on our x-axis, we have temperature in Fahrenheit, and then again on the y-axis, we have our SLR values. And you can see here, we can actually define a noticeable inverse correlation between the two, where as temperature increases, SLR decreases, which we would expect. Again, warmer temperatures generally produce denser snow, expect more sleet or ice events or freezing rain, as well as just denser snow in general. And that's confirmed here in our linear regression, where we can see that relationship between SLR and temperature. Again, our estimated and non-estimated data is all clumped into that nice downward trend on our plot. There's no outliers there that are really significant. We can see that all of our estimates and our non-estimates are clumped together. There's no defined areas of estimates or non-estimates, which again confirms that our observers are doing a good job estimating when they need to. It also shows that those have been representative for non-estimated values on the summit.
So for all of the figures that we've just been discussing, we're aggregating our 44-year data set and combining all of that. Now we're interested in looking through time, how is SLR changing? And so this figure shows exactly that. It is a time series where the x-axis is your years, your snow years. And then on one y-axis, it's your solid to liquid ratio on the left one. And on the right one, it's plotting temperature, because we found temperature to be significantly correlated, or I should say SLR significantly correlated with temperature. And from our results, we would be expecting that with an increasing trend in temperature, we would see a decreasing trend in SLR, because we found that they're inversely proportional. But what we found is that through our time series, both SLR and temperature are significantly increasing, at least in terms of their trend lines, which is sort of counterintuitive to what we found, which is a very interesting result. Although on an annual basis, they do line up as we would expect. As you can see, maybe in 1998, that was a particularly warm winter. For a very warm winter, we experienced a lower snow year. versus a couple of years after that, it was a particularly cold winter where SLR was higher. And so that inverse relationship does carry through on an annual basis, but interannually through trends, it doesn't necessarily translate. And then as with all of the plots that we've been discussing so far, we're plotting both estimates and non-estimated data. And we see two things really. Again, estimates don't have a significant impact on our results at all. Both tests, in terms of statistical tests, they test the same way. But what we do notice is that estimates really start having a noticeable impact after around 2000, 2002. Further analysis showed that that's really when estimates started ramping up. And that's something that we're currently working on a little bit more.
Yeah, and for those estimates, that was when estimates started being recorded more frequently on the summit. We do believe that there was likely estimates before that period of time. They just were not added to the logbook. But we don't have a time machine, so we will never know that for sure. So just to recap what we've been working on, as you can see from all of our figures, SLR at the summit of Mount Washington does deviate from that 10-to-1 standard set by the MWOBS, and that is used often in quantitative precipitation forecasts, meaning that the snow is really variable up here. There's periods of the year where we have really dense snow, which I'm sure all of you have seen before, in the shoulder seasons when you're expecting to have a nice hike, and then all of a sudden it is sleeting on you up here. And towards the winter, we do kind of get closer to that standard, but we still have snow that is slightly denser than that standard. So it just adds another element of uncertainty when we're forecasting up here, because using the models of 10-to-1 may not be entirely representative of what we're seeing in, any given day up here. And in addition to varying seasonally, again, SLR does also vary annually. So year to year, we are also seeing differences in our SLR, where some years we have a higher SLR because of colder snow events, and some years we have a lower SLR where there was denser, maybe more mixed precipitation events. And also what we found is that estimates are generally representative, which is great. It means that our data set can remain pretty much entirely intact, besides the initial filtering that we did, and those estimates are not ultimately impacting our work.
So we presented a lot of results, but our work is far from done. So a couple of things that we want to get started with in the future is figuring out what drives that temporal increase in SLR. So why is SLR increasing through time? Because we were very surprised. As I mentioned, that inverse relationship between temperature and SLR would have us expecting a very different result, yet that's not what we found. And there should be some scientific basis as to why we're seeing that. And that's something that we're currently investigating. Something else that we're interested in is looking at a more close case study analysis of SLR and whether particular synoptic setups have influence on SLR. We had a great presentation about upslope snow showers for sure. With different winter storm setups, how does SLR change? When we get a nor'easter, is that warmer, more humid air resulting in a different SLR than when we get an Alberta clipper that tends to be drier and colder? Does that have an impact on SLR? How are the frequency of these different storm tracks changing through time? These are all questions that we're very interested in exploring further. And then lastly, we've been talking about solid to liquid ratio. Ideally, we'd be looking at snow to liquid ratio, and that would involve differentiating solid precipitation and mixed precipitation. Especially in the shoulder seasons, it's certainly possible that we get a wintry mix, sleet events, graupel, all different types of solid precipitation that falls that isn't necessarily snow. And so we would like to go through our data set and try and figure out when it's only snow falling versus when it's a mix of rain and snow, when it's graupel, or any of these other solid precipitation types.
Great. So thank you all for listening to our presentation. If anyone has questions about this, we would be so excited to answer them. So reach out to the observatory. We would love to chat. But thank you.
Thank you, Maren. It may well have been, but at any rate, without further ado, Wanted to make sure we save time for last but certainly not least, summit intern Frank Vazano. Frank, take it
Oh,
away.
no. Let me share my screen. And can you see my screen?
Yes, I can.
Perfect. Let's see. All right. So,
Perfect.
all right. So, hello, my name is Frank Vazano. I'm a research intern for the Mount Washington Observatory, as well as the Appalachian Mountain Club and the Hubbard Brook Experimental Forest. This internship is one of the first of its kind, so super thrilled to be pairing with these organizations. And today I'm going to be talking about my research project that I've been working on for the past couple of months, which is going to be the White Mountains Climate Almanac. So here's a brief list of what we're going to be talking about today. So first of all, we're going to be talking about what the heck is a climate almanac, and then we're going to be talking about some of the research themes that are going to be present inside the almanac, and then we're going to be talking about some of the preliminary results. So what is a climate almanac? So if you're not familiar with what an almanac is, there is a definition here on the screen. In general, you're going to be looking essentially at, for each month, you may have certain either astronomical or meteorological averages and means and what we call normals. And essentially, we're going to be taking that concept and taking it one step further. So instead of just including, for example, temperature and precipitation here in the White Mountains, we're also going to be looking at various research themes for each month, alongside the monthly averages and extremes, and it'll also have some custom illustrations, which is very exciting. So here are the research themes that are going to be present within the almanac. So there's going to be 12, plus, of course, the extremes and averages section at the end. And I'm not going to talk about all of these. I'm just going to highlight two that I find particularly interesting. So I'm going to be talking about the March theme and the August theme. So here is the first bit of preliminary results that I'm going to share with you today. This theme is looking at how winter recreation days are changing over time. So what is a winter recreation day? Well, when I'm talking about a winter recreation day, mostly talking about people come from all over the place, thousands of people every year, to enjoy the various recreational activities that are available in the White Mountains. Particularly, I'd be talking about skiing, snowboarding, or tubing, anything that really requires a bit of snowpack to facilitate. And so essentially, we know that the White Mountains, winters are warming. They're getting less snowy, at least down in the valleys, and where people ski, maybe not on the summit, as Merritt and Mays have pointed out. But for most of the White Mountains lower elevations, they're getting less snowy. And so essentially, we're taking that prerequisite knowledge and taking it one step further and seeing how those changes are directly impacting winter recreation days. And so what really makes a good winter recreation day? Now, you can define this in many different ways, and this can be completely subjective. But there are actually some scientific metrics that we can use to determine the quality of a winter recreation day. So in general, you'll be looking at temperature, snowfall, and snow depth. So pretty much the most important thing is snowfall. You can't really ski if there's no snow on the ground, but also the quality and the quantity of the snow does matter. And the quality and the quantity actually does come down mostly to temperature. As you can see here, this is a chart showing how snowflake shapes and sizes actually depend on both the temperature and also how much water is in the air. As you can see, the water saturation is essentially the sort of the bang for your buck, if you will, how much snowflake you get out of how much water is in the air. As you can see, the maximum actually is right around 10 degrees Fahrenheit. So that is actually the answer for the trivia question earlier. And it turns out that these, what we call stellar dendrites, right around 10 degrees, are actually the best snow for skiing and snowboarding in general, because these kind of snowflakes are basically not very dense, and so they're pretty bouncy, and so they are essentially what we call powder for a pow day. We're also going to be looking at, so essentially, the daily temperature. We're going to be sort of using a proxy because snow doesn't necessarily get created right on the ground. So we're going to be looking at about 20 degrees on the ground and going up from there. And as you go up in the atmosphere, the air will cool. And so it'll be a little bit colder up above you where the snow is being made. And so we're going to take a good proxy at about 20 degrees Fahrenheit. We're also going to look at how daily snowfall is changing. So if you're looking essentially at greater than 1 inch, then that's going to be a good snowfall day. And then if your snow depth is over 8 inches, then that's going to be a good snow depth day. And essentially, we're going to be calculating a score for each day in the winter and then summing them for the year. And this is the results. So when applying that to data, this is data from AMC Pinkham Notch Visitor Center back to the 40s. So they do temperature, snowfall, and snow depth. And essentially what we're seeing is an unfortunate trend where we're seeing that, but expected, as I mentioned earlier, since our winters are warming and getting less snowy, essentially we are going to be seeing less ideal winter recreation days over time. And it turns out to be about, you're losing about 2 and a bit more recreation days per decade, which may not sound like a lot, but that definitely does add up. For example, I mean, essentially if you follow the linear trend, if you were in the 2020s, you're going to have essentially 15, 16, 17 less recreation days than you would in the 40s, which is, 2-3 weeks, which, across the whole winter, that adds up, and that is quite a lot. We can also break it down by decade and month. And as you can see, a lot of that loss is actually happening in the so-called shoulder seasons, which is generally December, and then also March and April. And this is most striking here in March and April, where you can see that there's a pretty severe decline in the amount of winter recreation days that are happening in these months compared in the 2000s and the 2020s versus earlier in these period of records. And this is also a little thing that I put together just for fun, just to see what is statistically the best week, I suppose, for winter recreation days. And this is just over the past 30 years. So if you're curious, these winter recreation days are sort of backloaded right onto the end of winter for the most part, right before astronomical spring starts. So it turns out that the best week is February 15th, and it's just a hair better than March 1st. But in general, our best skiing conditions are going to happen right around end of February and beginning of March. Okay, and this is the second piece of preliminary results I'm going to be talking about. So this is the August theme, and sort of as a nice mirror to the March theme, this is looking at summer recreation days. So unlike winter recreation days, summer recreation days do not depend on snow at all. And so summer recreation days are a little bit more tricky to define because there's quite a lot of different activities that you can be doing. So for example, you could be hiking, or you could also be swimming. And if you're swimming, that's going to basically swimming in 103 degrees Fahrenheit outside is going to be a lot nicer than hiking in 103 degrees Fahrenheit. And so essentially for this theme, we're going to be talking more about the former, which is hiking. So essentially thinking about summer recreation days, we're going to be talking about hiking, camping, biking, that sort of stuff happens on dry land. And so what really makes a good recreation day in the summertime? The National Weather Service suggests that you should take heightened caution if the temperature is above 80 degrees. And I think it's, even more, as it goes higher up. But essentially that's going to be sort of a cutoff. If a day is less than 80 degrees, it's going to be a very good summer recreation day. And it's more than that, it's going to sort of slowly drop off towards 0 points. And then we're also going to be looking at certain weather types that may impact these recreation days. So for example, rain, hail, and lightning. So these are all very important to keep in mind while you're recreating here in the summer in the whites. And these events can basically make or break your day. And so very similarly to the winter recreation days, we'll be calculating this for every year and then summing them up year over year. And this is essentially what we get, sort of a similar looking graph. This data is once again using AMC Pinkham Notch, their daily temperature, but also Mount Washington's rain, lightning, and hail data. And as you can see, there is a less striking trend, but definitely a downward trend, which is equally as unfortunate. ends up being about 2/3 of a recreation day per decade, which does translate to about 5, 6, 7 days over the period. We can also break this down by decade and month. And as you can see, there is quite a lot of that downward trend. Is actually coming in June and July. These months are essentially getting warmer, more warm than August and September. And they're also getting lightning days are also increasing, and rain, although rain days are remaining the same, we're seeing essentially rain intensity increasing. And so it seems like September and August are a little bit more resistant to that trend. And a similar thing did for this one. This one's a little bit cheaty since they're sort of September and August are pretty much automatically going to be a nicer day on average, a bit cooler and a little bit less rainy. But as you can see, the statistically best week is apparently September 14th. All right, and that concludes my presentation. So if you have any questions, go ahead and drop them in the Q&A, and we'll try to get to them.
Excellent. Thank you so much, Frank. Really appreciate that. What I'll do is I'll see if I can switch everyone's views. We can switch around to look at the gallery of all of our interns who I'd love to welcome to. Feel free to turn your cameras on. You can unmute yourself if you'd like. And as Frank was just suggesting, for those of you participating on Zoom, feel free to drop your question into the Q&A button that you'll find at the bottom of your toolbar, and we'll see if we can get to as many as we can. And certainly we'd be happy to follow up with any questions that we don't get to this evening. So yeah, first and foremost, I know there's just a couple questions in the chat here, folks really actually wanting to get to know each of you a little bit more. I know, Peter, you spoke to your background a little bit, but I don't know if we can just go around the horn maybe once and everyone just kind of share out again, or for the first time, just anything personally like to share about yourself, including your field of study, where you're studying, and if any hopes and dreams or aspirations in your work and studies, feel free to share. So I don't know, Peter, if you want to reshare what you started with.
Sure, yeah, I can kind of go even further back. Then I think I pretty much stopped at my education and my internship here. So I'm from Massachusetts originally, central Massachusetts. I've had an interest in weather and especially winter weather ever since I was really young. I think I began to really become interested and motivated to learn more about it around the ages of 4 or 5. I didn't really understand what was going on, but I knew it was something that piqued my interest and excited me. So eventually that led me down the road of atmospheric science or meteorology. And sure enough, I loved it when I started going to school for it, and decided to go to get my master's, which I'm currently doing right now. I did some work with climate modeling in my undergrad. I started doing that for my thesis for my master's, but I think I might take this project and continue with it instead for my thesis. As it's working on climate modeling was interesting. It was something I was really intrigued with heading into school. But I think as I took all the classes and continued with them, I think I kind of got back to my roots, which is, kind of the mesoscale or smaller scale features and local climate features and microclimates. And I think that's, being up here in Mount Washington and getting the opportunity to just kind of do my own thing and start my own project further cemented that. So, yeah, and I think like for my future plans, obviously finish my master's now, maybe continue with grad school. And if not, I'd like to work at the National Weather Service or the Climate Prediction Center, or perhaps in private industry as well. All those things interest me, and maybe I'll do some of each. Who knows? So, but yeah, that's pretty much my background.
Awesome. Thank you, Peter. Appreciate that. Learned a few things there myself. Yeah, up to the summit, Marin, Mace, if you wouldn't mind sharing a little bit.
Sure. So again, I'm Marin. Oh, thank you. I actually grew up in Massachusetts as well, so spent a lot of time in my youth up here in the Whites. Then moved to Colorado for school. I did my undergrad and I'm now finishing my master's at Colorado State University. Go Rams. So it's great to actually get to be back up here on the summit exploring the mountains I grew up in again. At CSU, I've done both my degrees in watershed science, and my focus has been in snow hydrology. My master's research has mainly focused on remote sensing applications for snow water resources, so using satellite data to look at snow. So it's been great to actually get to be on the ground here and not just be staring at my computer all the time, actually playing in the snow. When I'm not up here on the summit, I'm also working for the Mount Washington Avalanche Center. So that's been great to really dive into the snow, do a lot of work with snow science and submitting observations. So in terms of my future, I would love to get to stay kind of in that realm or some sort of research related to snow hydrology. But yeah, that's kind of where I'm at right now.
Thanks, Marion.
Yeah, and I'm Mace. My dad was a geologist, and I actually had a non-conventional upbringing. I grew up all over the world. I was born in New Orleans, and I've lived in Egypt, Malaysia, the Middle East, as well as the Texas Gulf Coast, and that gave me a really just huge fascination with how the Earth as a system works and how different climates come into being, and how all of that works together. And that sort of, when I applied to college, drove me to pursue a degree in atmospheric and oceanic sciences that I just graduated from. I graduated from McGill University in Montreal. Now I'm taking sort of a gap here, doing this internship before starting my master's in London. Yeah.
Oh, that's awesome. Thanks, Mace. And what about you, Frank?
Yeah, so I'm from Colorado. I grew up with the Rockies in my backyard pretty much. I'm from Colorado Springs. I went to the University of Colorado in Colorado Springs, which is part of the CU Boulder system. I've always loved meteorology and climatology, and I'd never been to New England before, so I'm very psyched to come up here, and I love Mount Washington. So after I finish this internship, I will be going on to get my master's in meteorology at the University of Oklahoma. And after that, I hope to be working in climate or weather research.
Excellent. Thanks, Frank. Thanks to each of you for sharing a little bit. I know folks are always curious, the pathways that folks go on through here, and certainly we'll all be excited to see where you go on from here. No pressure. But to bring it back to maybe some specific questions just from some of the audience here that have come in around some of your work and presentations. Again, I know we won't get to all of them, but just a really practical question here, a great one from Mike, and this one's for you, Peter, regarding upslip snow events. Can they occur with an easterly wind, or is it only a westerly or that northwesterly component you were talking about?
Yes, they can occur with easterly winds. Basically, if a storm comes up the coast, like a nor'easter, it can cause upslope snow with a northeasterly or easterly wind component. Those seldomly happen. I think there's a couple in my data set that I put in, but a vast majority of events coming out have winds coming out of the west or northwest. So it's mostly what I talked about today. But they can absolutely be generated with easterly winds.
Yeah. Okay. Well, and so yeah, lots of questions that I had around those pieces. But yeah, I guess like you said, and presented on for some of those case studies, you're going to see kind of the wraparound with cold air coming in from the north and northwest, and and then sort of the orographic uplift, like you talked about. Gets cold though from every direction, I suppose, and certainly we've seen high winds as well. Question for Marion and Mace, where one, I mean, I was just really fascinated personally, even just with your results and the fact that it wasn't necessarily right around the 10-to-1 ratio, or even actually higher than that. And Jerry here left a comment and a question. He said, we had a fairly cold January this year, and we had some days at Bretton Woods, down at a lower elevation with 20-to-1 SLR. It seems like you didn't see that at the summit, and I'm kind of in the same boat. Like, what gives?
So there's a lot of reasons that could be the case. One of them is that we do have really high winds up here, and so sometimes that means we're getting undercatch, or the dendrites are breaking down in the air as the wind is pushing them, and that can increase the density of your snow or give you a lower SLR. That isn't to say that we don't have 20-to-1 events up here, but they are less frequent than lower density or higher density events. So that is to say that even though our average SLR is more of an 8-to-1, that doesn't mean we don't have 20-to-1 events. I know a couple of the days that we've been up here this season, we've definitely had that happen. You want to add to that?
No, nothing to add. You answered that perfectly.
Yeah, no, and it's just, and from my experience on the summit and measurement as well, I think those like 30 and 40-to-1 scenarios, I can recall some of those because they're so, bizarre, I think, at least for New England anyways, but still was kind of floored that you're finding your mean and median lower than that 10 number. Also, since you're on the summit, I'm curious. I guess we could all look on our current conditions page. Sue is kind of curious. Hey, what's the wind speed there right now? It's howling in Champlain Valley in Westport, New York. I know I was looking in North Conway here. It's getting windy, but since we have you on the summit,
So for those that have read the forecast, you would know that we're in the clouds right now. We're experiencing somewhat of a winter storm. Winds currently are almost 58, almost 60 miles per hour sustained. We're also getting a lot of snow. Some of you might have seen me check my phone. We're getting probably the most snow that we've seen this internship so far, which is very exciting, especially when our research project has been so focused on snowfall on the summit. So that's very exciting. But yeah, wind sustained at 60, gusting probably over 75. It's getting hairy out there for sure.
Definitely some blowing snow going on.
Yeah, definitely some blowing snow.
blowing snow. Yeah, well, even down in the valleys today too. Um, Frank, I have a question for you here, Mike, or even a comment from Mike who mentioned around winter recreation days, suggesting, hey, one more variable. It might not be as significant at valley elevations, but for the summits, it might be interesting to include wind speed as a limiting variable. Is that something that was kind of talked about, or what are your thoughts around that?
No, definitely. I think for both of these themes, there's actually quite a lot of other metrics that could go into it. For example, I would love to have included humidity for the summer recreation days, but the data is difficult to come by for lower elevations. But Mike makes a great point about the wind because that makes a big difference. If you have a lot of snow, it doesn't really matter how much snow you get if it all blows off, right? So essentially, and that was definitely thought of. Um, I think essentially what this part of the research was specifically focusing on was sort of your lower and middle elevations, because I think you could realistically, if you're talking about higher elevations recreation, that could be an entire thesis, because it would be yeah difficult because we already know it's difficult one to measure snow. And also just how quickly the conditions can change up at the higher elevations. So in general, this research would be looking mostly at the middle and lower elevations, but definitely if I was to look at higher summits, that would be something I would consider.
Excellent. Thanks, Frank. And before I forget, give you the plug. I know you'll be participating as a panelist at New Hampshire Public Radio's third annual By Degrees Climate Summit that's taking place on May 2nd. So if you're out there and you want to hear more about Frank's work, he will be helping to support a panel conversation around it. So yeah, very much looking forward to that.
Thanks, Brian.
Great question. A good plant question I know from a researcher here named Sarah. Hey, these were great presentations. What was your most memorable days working at the summit during your internship? And maybe give you all a second to think about that. Peter, I don't know if something comes to the top of mind, because I'm sure you have some memories to choose from.
Yeah, there's a few to choose from, but I think the one that stands out the most, I think always will be my second day on the summit. Um, we came up there, expecting extreme winds. We ended up getting gusts up to 142 miles per hour on our second day, which is, like the observers told me, like that's pretty rare. And I think I broke some of the observers' wind records that have been up there or personal bests that have been up there for 2 or 3 years. So that was definitely memorable. And I think getting outside, experiencing 100-mile-per-hour sustained winds and gusts to 120, and then getting up on the tower, or trying to get up on the tower, I should say, grabbing onto the ladder while the wind's trying to peel me off. I think, yeah, that's a memory that's always going to stick with me. But I think number 2 would be rescuing the northern sweat owl on the summit as well. I know that's on the Mount Washington's social media pages. I think that's number 2, but I think being, in love with the weather, I think number 1 will be that extreme wind I experienced the second day.
Yes, who knew you would be also animal wildlife caretaker there. Great serendipitous story and outcome. And if you don't know what I'm talking about, you can search Mount Washington and owl in Google, and you'll find out a little bit more. Mace, what about for you and Marin? What are some days that stand out?
Yeah, I think I can speak for both Marin and I. Our wind record, we had a day where we got 138 miles per hour. And that was also the day we decided to sit on our butts on the deck and get blown by the wind across the deck, essentially playing Mario Kart. and that was actually captured by the deck cam, by the live cam, and that went completely viral. We had stories on CBS, CNN, the Weather Channel, Outdoor Magazine. I got close-up shots of me all zoomed in, struggling on the ground. Very embarrassing, but a very, very memorable experience for sure.
That's excellent. Yeah, Mount Washington will certainly humble. And Frank, what about for you?
Yeah, I'm sorry to one up you guys, but I was here last month in February for the 161 mile per hour gust. That was definitely probably the most memorable. Watching the haze chart was probably more interesting than watching the Super Bowl this year. Just seeing how high it would go. The haze chart tops out at 150, so pretty much broke that and many multiple times, and we weren't really sure how high it went at one time, but or at any given time, but until that 161 came in, and that was the moment. It's like, yeah, that's pretty strong wind. So that definitely broke my record. Broke a couple of the observers' records up here too. So yeah, I'll never forget that day.
Yeah, highest wind I think in 6 years. So pretty impressive stuff. Well, and so for the audience, in case it's not obvious to you, Marin and Mace are on the same shift here. It's a Tuesday. They're getting near the end of their shift week. Tomorrow is shift change day. So Frank and Peter, they're on the same shift. They'll be headed up the mountain tomorrow to continue their work. They'll be wrapping up their internships soon. But more work certainly to come. And I'll just might leave it right there. I know we have more questions that may not get answered here. If you're interested in reaching out, want to get your questions answered, I'm happy to direct you to all of our presenters from tonight. You can reach out at education@mountwashington.org or go to mountwashington.org and find the Contact Us page. Just really love to say thank you to each of you, Marin, Mace, Frank, Peter. Excellent work. Really grateful for everything that you bring to the observatory, all the effort, the professionalism. Hope in turn that this has been valuable for you guys. Big thank you to our science committee members who volunteer in addition to help guide some of these projects, in addition to, I know, the other staff, observers, Mike Carmen, Jay Brocklow help support a lot of these projects as well. And so just really grateful for everything that you've brought to this work. With that being said, for the rest of you who have joined the program tonight, if you enjoyed tonight's free program and are interested in supporting the observatory to keep programs like this free, we'd certainly welcome your donation and support over at mountwashington.org. You can find the donate button that's in the upper right-hand corner. Also, if you have any feedback, constructive, positive, whatever, for our speakers for tonight, or thoughts about future Science in the Mountains programs, we'd really encourage you to fill out the Google Form survey that'll show up in the Zoom window following this program, and also in the follow-up thank you email that comes out tomorrow. And then finally, don't forget to join us for next month's Science in the Mountains program. It's on Tuesday, May 20th at 7 p.m. Now and Then, a history of the Mount Washington Carriage Road and Glen Houses, and that'll be presented by Howie Weems, former Mount Washington Auto Road General Manager and Glen House partner. So don't forget to register for that program. You can watch any of the previous programs you may have missed over at mountwashington.org, and looking forward to having you join us for another program. Thank you again, guys. Really appreciate it. Have a great night, and hope to see you on the mountain soon. Take care, everybody. Night.